Hey, what's up everybody, it's Ivan here. And this new series, it's kind of gonna be like, imagine that you're walking down the street, like minding like your own business. And somebody walks up to you and says like, hey, you the person, can you go ahead and build and train the simplest, most readable GAN that can generate faces using Keras possible? And if your answer would be no to that question, this is kind of where the series walks in and kind of is designed to help you do exactly that. So, and it's gonna be pretty different from also any sort of other series that I've done on this channel. But first, let's check out, what kind of faces am I talking about. So, something like this, simple faces, not the best looking, but the ones that do the job, And you can also we'll also explore how you can do some cool demos and play around with the input noise and how changing that, affects the images. You can check out some different faces here, how they're getting transformed. But again, they're not the best looking, but the purpose of the series, I like to think, is to actually go from zero experience with GANs, which is where I started a couple of weeks ago, to being able to understand and build something that can generate faces and understand the code. And when it comes to understanding the code, obviously Keras is one of the top players in the games with its readability. So pretty cool faces, not the best looking, but that do the job essentially, right? And we'll also see how the training process is happening and how those faces actually come to be, and I'll share a bunch of tips and tricks because my knowledge about GANs pretty much right now, it's this much theory and that much trial and error on this project. So hopefully I'll be able to bring some value with that. So we'll look at the training, we'll cover that, cover some, cool demos that we can do with it. And I'll also be showing how you can work on this problem with two data sets, one of which is pretty simple. It's just a bunch of faces faces that are similar to each other. But also I'll show you how you can load and use for this purpose the IMDb wiki dataset, which is awesome, and I've made a video on that dataset in the past, but just the quick thing about it is that it's 450,000 images of celebrities, and you can sort the images that you want by gender, by age, so a lot of variability on what type of images you want to bring into your problem there. So, and talking about how this series is kind of going to be different from all the other series that I've done on this channel, because usually I had some sort of project, right, that had been done, and I would just go ahead and explain the steps of going there. So in this case, I'm kind of trying to learn about GANs myself, and not necessarily knowing what's the best way to do things. And while that, I've also pretty much spent the huge chunk of the last couple of weeks, I gotta say, with a lot of trial and error, different data sets, different architectures, different approaches to training. I pretty much, tried a lot of stuff that I'll share to hopefully have here the simplest thing that, you can just look at the code, look at these things, see the results, and be like, hey, I didn't know much about GANs, but I guess now I kind of understand the basics. And because I'm also learning, I'll be doing my best to credit the sources that have helped me the most in this learning process, here at the top, huge credit to Jeff Heaton, awesome channel. My notebook here, it's based on the notebook that he provided in his videos, but here I've modified a bunch of stuff, and the architectures, after a lot of trial and error still, but the architecture that I'm using here is inspired by Mitchell Jolly. Here's his GitHub link, basically. So in this video, we'll focus on the data, right? On the data of where do these faces here come from? And again, they're not great, but the purpose, I like to think, is again readability and understanding. And obviously, if you can do that, then venturing out to something more complex becomes a lot more plausible right? So we'll talk about the dataset now. So the dataset that this demo was trained on, it's actually the same dataset that Jeff Heaton provided initially in his notebook, right? So this is a dataset it has about like 8-something thousand images. And as you can see here, right, the images are, especially compared to IMDb Wiki dataset, right? This is a lot simpler dataset for several reasons. Like, first of all, the people are looking straight at the camera, and you can also see an interesting detail here is that people are like, it's like pretty much a lot of images of the same people. So while there are a lot of images, the amount of actual unique faces that are being presented to the GAN is a lot smaller. And so when we look at the results here in the demo, like, you can see that a bunch of backgrounds are either they're like brown, like here, or they are green, bunch of greens, browns, and also some of this, bluish backgrounds here that are also obviously coming from this data set. So the interesting thing about like this way of training a GAN to generate faces is that, right, because like it's something that I was not kind of used to, because usually when we're talking about training data in computer vision, we have images and then we have labels, whether it's like object detection labels or whether that's classification problem, like the most typical MNIST, right? You have like the picture of a digit and then you have its label. Here, like, the coolest thing is that all we kind of gotta do is to get bunch of images of faces, or by the way, this thing also should work on like, I don't know, like nature images or like cars or whatnot. So you just get the data, and then those two neural networks, the generator and the discriminator, in their fight to outsmart each other, kind of learn some meaningful patterns along the way, and the generator that obviously has to fool the discriminator tries to generate the images that the discriminator would perceive to be real. But we'll dive into this whole topic much more deeper. Now it's about the whole data thing, right? So again, the cool part here is that it's unsupervised learning. So we just got the data and we're basically, throwing the data at the generator that's creating the images and the discriminator that's trying to find which images are real and which images are fake, and then pass that knowledge to the generator so that guy can get better and the circle continues. So yeah, that's the type of data set that we're looking at, right? So, quite a lot of faces, but again, a lot of faces are repeating here. Yes, so now let's actually go to the notebook here. So I'll leave the link to this notebook in the description, both on Colab and GitHub, wherever you wanna, use this code. Now the next cell is something that's familiar to probably everybody that uses Colab. This is the cell that we used to mount into Google Drive. I have the whole video on this relationship between Colab and Google Drive, but in brief, they're very integrated. So essentially, the way that we get the dataset in our Colab is that we first save it in our Google Drive, and then we go ahead and copy it from, or not copy, or just unzip it from our Google Drive into the environment of the notebook. So I have a video on that. It'll pop up somewhere and it'll be in the description, but essentially I've downloaded the dataset and I've put it on my Google Drive there. So then we can go and create the images folder where we'll place images, and here's also the command that deletes the images folder, because this can be useful when you're messed up your images folder and you kind of just want to get the new one and unzip the new data there. You know what I mean? Yes, and now once we're mounted into the Google Drive, the next thing we do is here's a bunch of stuff that I wrote here, but basically it's the link to this dataset on Kaggle. You can go here on Kaggle and download it. If for some reason you don't have a Kaggle account or you do not have access to that right now, I've also put the dataset on my Google Drive, so you can just go download it and then upload it to your Google Drive, right? But for instance, in my case, in my Google Drive, it sits in the folder that's drive, my drive, GANs, images.zip. So if I run this command, it'll essentially unzip it, right? It'll unzip it here, and it's actually going to be a lot of images there. But yeah, it'll basically unzip the whole thing in the environment of this notebook. And by the way, for those of you wondering, like, what's this thing about? It's the command that suppresses the output of a cell in Jupyter. So basically, it would be writing like all the files that it's unzipping, and it's kind of messy. So I just like suppress the output of this cell here. Now, right now we can go here, and here's the IMDb wiki code. We can skip it right now. First thing we can do here is check the length of the images folder, and it's 7,800 images in this case, right? And here are a few commands I got that can visualize what's actually inside of the images folder. So this command, this function here, it's able to display the image, right? And so if we like run this cell of code here, that's essentially, and let me, oh, it's already got a comment, you know. Pretty thoughtful mind, I guess. That's essentially displays a random image from the images folder, right? It displays the random image from the images folder, and you know, and the images folder on Colab pretty much looks like this. You know, it's pretty much this, you know. So when we're displaying the images there, it's kind of like to make sure that again, because the data set is not that diverse, you know, we're not like really exploring much of anything here, but it's more like, you know, we're just making sure that the images are there and that everything's working. Now, I've skipped a line of code here, and not only the IMDb wiki part of code, which is the larger data set of celebrities that you can also work with, but also the line of code that is this guy. And so what this line of code does is it's essentially data augmentation, right? We basically go over every image in the images folder, load it with OpenCV, and then we mirror it. Like we flip it, you know, along the, the vertical axis, I guess. So it's essentially like it's mirroring the images. Now, because I thought, I mean, look at this, right? If we're dealing with a data set whose apparently entire purpose is that it has a lot of images of the same faces in different variations, then like why not go ahead and like just mirror them and get even more images that are of the same people, right? So like the amount of unique faces stays the same, but we get just like more variation, right? In the way in how we got all these faces. So just like a bit of data augmentation. So let's run that. And remember, we had 7,800 images, and by the end of that, we'll end up with probably like 15,000 something. Yep, 15,000 images. Yeah, like these images, just all of them also mirrored. You know, pretty simple stuff. But the OpenCV is so cool, like it does that like so fast, you know, pretty cool stuff. So now the last thing we gotta do with our dataset, right? We got all the images that we want to work with in our images folder, but then the other thing that we gotta do now is to actually load them, and is to load them into a Tensorflow like dataset format, right? So to do that, we first define a few things here, and the only relevant thing for the data part is that we're gonna be generating images. Like these images are in the 128 by 128 resolution, so that's why they are, you know, not in the best resolution, right? But this sort of does the job, right? For the way that we frame this problem, you know what I mean? And yeah, it's basically gonna be like 128 by 128, so and 3 channels, obviously. So yeah. And so here's how preprocessing is happening. So we import OpenCV as CV2, and we get this training data folder. And essentially what we do now is iterate over every image in the images folder and load that here with OpenCV. So we load that image, and then right away we resize that to be in the in the resolution of 128 by 128. Oh, by the way, check it out. Colab is so cool, it actually says what's the value of the variable is here. So it's 128, 128. Pretty cool stuff. You know, I've actually just noticed that. Yeah, and so then I convert, because OpenCV, every time it loads an image, it loads it in like BGR. I then explicitly convert it to RGB for our use here, right? And here's some code that's, you know, in the IMDb wiki dataset, some images are, because it's like such a huge dataset, and a lot of the images there, not a lot, but some of them are grayscale. And so obviously when we're, and you know, we don't want to use the grayscale images, but you know, but we also can't use them because here we're resizing our data set, right? We're resizing the you know, we're reshaping our list with all the loaded images into a 4-dimensional tensor that'll be used as the that'll then be converted into a TensorFlow dataset thing, right? Basically, you know, you cannot put together 2-dimensional images, which is like, you know, just the height and width, and the 3-dimensional images that are like height, width, and also the depth of the channel stuff. So we're kind of like here essentially saying that, hey, if the image does not have 3 channels, you know, we ain't want to do nothing to do with it. So we basically like just skip it, right? So we end up with this training data list of images. Then we reshape that into a 4-dimensional tensor, right? That'll have the first axis will be basically, the first dimension will be like the amount of image that we got, which is like 15,000, and then it's pretty much the 128, and then 3, which stands for the image channels. Colab, come on, you've been showing me the values of the variables. What happened? Yeah, it's 3. Cool. So then we type it to the NumPy float type to then do the pretty much the main pre-processing step here, I would say, because we're essentially, and also a really simple one, because if you remember the, you know, the pixel values of the images, right, of the 3, what is like the RGB images, right? We have basically the red channel, the green channel, and the blue channel. If they're all 0, it's the color of that pixel will be black, and if they're all 255, it'll be white. And for instance, this will be a red pixel. So what we're doing here is essentially saying like, hey, like kind of like squish all the values of the image. It's called normalization. Essentially, like squish them to be between 0 and 1. So now the black color would still be 0, 0, 0, but the white will be like 1, 1, 1, and some sort of like grayish color would be like 0.5, 0.5, 0.5. So it's really typical pre-processing. Why that matters? One word as to why that matters is because our generator here uses the sigmoid activation function. So the images that will actually be generated will be, you know, in range from their pixel values will be in range from 0 to 1, right? There will be, you know, not normalized in this way, and to allow the discriminator to basically look at them equally, you know. So we have our training data pixel values from 0 to 1, and also the stuff that's getting like generated by the generator from 0 to 1 to match the sigmoid activation function. Whew. And yeah, I guess we like run this code here. Should be pretty fast. Again, OpenCV is amazing. Like, look at it, like 1,200 iterations per second. Whoa! So it's basically like processing, you know, loading and resizing and changing colors and dividing 1,200 basically images per second. It's really cool. And then we, you know, essentially from that list of images divided by 255, we essentially turn that into a TensorFlow dataset from slices, training data we'll specify here, and then we shuffle it with our batch size, which is 32 in our case. Yeah, and we specify also the batch size here. So, and this pretty much gives us the dataset. So again, it's a 4-dimensional thing, because that's how the dataset for ConnectNets are. Now, one thing to be on the lookout for, I use here the, so essentially if you, the way the dataset is loaded here into the memory of the network, like the dataset is actually stored in the RAM, right, in the RAM, when we're training. So if you have too many images, you know, on call-up, you can essentially have your session crash because like you've ran out of RAM, for instance. I'm pretty sure that this amount of images is safe, like about like 30,000 images seems to be a safe amount. Here we got like 15,000 something, right? I'm using high RAM setting here, but it's also should work. This amount of images should work on the low RAM setting on call-up. But the main thing here, you know, if for some reason you use a lot of images and your call-up notebook crashes, like make sure that you know, just kind of like either you can do a Keras generator that loads the images from the hard drive, or just kind of like lower the amount of images that you put into RAM. Like it's hopefully that'll save some time. And yeah, pretty cool video, right? You know, we've pretty much, you know, a step closer to being able to do our kind of simplest Keras readable GAN possible. And it's been a lot of fun for me, and I hope it's also a lot of fun for you. So, you know, thank you guys for watching. You know, smash that like button, you know, if you're enjoying these videos. It really lets me know that you guys are excited and that I'm helping you. Also, please subscribe to the channel to show the same thing and plus get notified when I release new stuff. If you want to support me, some ways to do that are in the description. Thank you so much if you do. And yeah, just like hope you like my new background here, you know. And I hope that you enjoy these videos, and especially I hope that you guys, you know, that you guys are safe, and that really, like, you know, your loved ones are safe, because the whole pandemic thing, it's not over. So hope you guys are safe and your loved ones are safe, and I'll see you in the next video.